When you're standing on a busy train platform, you probably don't think twice about those glass doors separating you from the track. You just trust that they're going to work. But that trust, it's not an accident. It's actually the result of an incredible amount of invisible engineering, a super meticulous process of predicting and preventing failure. So today, we're going to deconstruct the actual safety analysis for a brand new monorail to see exactly how that safety gets built from the ground up.
Okay, so let's just dive right in. The big question, the one that every safety engineer lives and breathes, is this: how do you stop a disaster before it can even happen? It's kind of like being a detective, But instead of solving a crime that's already happened, your job is to imagine every possible way things could go wrong, and then stop them in their tracks.
So here's our roadmap for this whole investigation. First, we're going to start with the massive real-world project at the center of all this, the Cairo monorail. Then we'll zoom way in on one critical piece, those platform doors. We're going to uncover the special tools engineers use to hunt for hidden failures, learn the language they use to actually measure risk, see the final verdict from their tests, and then pull it all together to understand the bigger picture.
All right, so our story starts in Egypt, with one of the biggest urban transport projects happening in the world right now, the new Cairo monorail system. And just to give you a sense of the sheer scale we're talking about, the two new lines being built will stretch for a combined 98 kilometers. That's a massive new artery for the entire city. And this new network, it's going to connect 34 brand new stations, moving millions of people. I mean, the complexity is just immense.
So how in the world do you make sure every single part of a system this big is safe? Well, the answer is kind of buried in a dense, super technical document, the official fault tree analysis for the project. And this is our case file, the blueprint that holds all the secrets to safety.
Now, obviously, we can't analyze all 98 kilometers at once. So just like any good detective, we're going to narrow our focus to a single, critical piece of evidence: the platform screen doors.
In the engineering world, they call them the PSDS, or Platform Screen Door System. We all know them as that wall of glass and steel that keeps the platform separate from the tracks and, more importantly, keeps passengers safe from moving trains.
The official purpose, and this is stated right in the analysis, sounds deceptively simple: to protect passengers on a platform against hazards of moving trains, right? A very clear, very simple mission. But making sure that mission succeeds millions and millions of times without a single failure, that is incredibly complex.
So how do they do it? To get that level of safety, engineers have to find problems that don't even exist yet. And for that, they need a special investigative tool to hunt for every single conceivable way the system could fail.
And that special tool is called a fault tree analysis, or FTA. Now, instead of looking at a part and asking what could go wrong, it works completely backwards. It starts at the top, with the disaster you want to prevent, like the doors opening at the wrong time. And then it maps out every single event or combination of events that could possibly lead to that disaster.
As our source document puts it, the entire goal is to chart the path to failure. Because if you can understand every single branching path that could possibly lead to a serious hazard, well then, you can design specific safeguards to block each and every one of them.
So, how do you actually draw this map of failure? You use a simple but really powerful language. An AND gate, for example, means multiple things have to go wrong at the same time. Think of it like this: for your toast to burn, the toaster has to be set too high and you have to be distracted. An OR gate, on the other hand, means just one thing needs to fail. The smoke alarm goes off if the toast burns or if its battery is low. With these simple rules, engineers can map out incredibly complex systems.
But hey, this isn't just some thought exercise. It's a super rigorous, data-driven process. First, you define the disaster. Then you build the map. And then, and this is the critical part, you plug in real-world failure rate data for every single component. From there, you can actually calculate the statistical probability of the disaster ever happening, and then check if that number is small enough to meet the project's safety target.
And that brings us to the language engineers use to talk about these targets. Because in safety engineering, risk isn't just a feeling, it's a number. It's a quantified, calculated, and strictly managed value. The key term here is the Safety Integrity Level, or SIL. It's basically a rating for how robust a safety system needs to be. The greater the potential harm from a failure, the higher the SIL rating required. The scale goes from 1 up to 4, with SIL 4 being the absolute highest, most demanding level of safety.
And those ratings correspond to some staggering probabilities. A SIL 2 system, for example, needs a failure rate below 1 in a million per hour of operation.
But for the most critical functions, the ones assigned SIL 4, the tolerable hazard rate has to be less than 1 in 100 million. That is a mind-bogglingly high standard some of these systems have to meet.
So, we have the method, and we have the safety targets. It's time to see the verdict. After all this analysis, did the design for the Cairo Monorail's platform doors actually pass the test?
Well, the results from the analysis are laid out right here. For SF1, that's preventing the doors from opening unexpectedly, the requirement was the highest level, SIL 4. The verdict? Target met. Yes. For SF3, making sure the closed and locked signal is always accurate, another SIL 4 requirement. The result? Yes. For every single critical function, the calculated failure rate was lower than the incredibly demanding target.
So the conclusion to our whole investigation is clear, and it's really satisfying. After mapping every conceivable failure and running all the numbers, the final report states that all assigned SIL requirements were achieved. The design is certified to be as safe as required. It passed the test. Okay, so now that we've seen the verdict, let's zoom back out from all the technical details and ask the most important question of all. Why does this matter?
This right here is the blueprint for safety. It's a proactive philosophy, not a reactive one. It's a way to hunt down and eliminate failures before they can ever cause harm. This meticulous, invisible engineering is what ultimately builds our trust in public systems, knowing that every single component has been mathematically stress-tested long before it ever becomes part of our daily lives.
We've just peeked into one small part of one safety system for one monorail. But this level of rigorous, proactive design is happening all around us, all the time. So the next time you step on a train, get on a plane, or even just walk into an elevator, it's worth asking yourself, what other invisible systems are working right now to keep you safe?